Okay, so all of Chapter 2 is about sets. So 2.3 continues the items that we're working with, sets, and we're going to talk about set operations and Cartesian products. All right, so set operations, there's several. The first set operation we're going to look at is called intersection of sets. So here's our definition for intersection. The intersection of sets A and B, and it's written sort of as an upside down U, or it looks kind of like an N, you know, the curved part of a lowercase n. You want to think about N for intersection. It's the set of elements common to both A and B. And this is the set notation for it. It says the intersection of A and B means that X is in A and X is in B. So a couple places you've seen that phrase intersection used before. Mathematically, you've probably seen it in terms of intersection of lines, right? It means lines that cross. The intersection is the point where they cross. In maybe driving language, you know what an intersection is. It means the same thing. Right? The intersection of Kickapoo MacArthur out here is exactly where the streets crossed. And in terms of the language we're using here, both of those fit this description too. Where they cross means things they have in common. So when we're talking about lines, it's the point they have in common. When we're talking about the streets, it means the portion of the street where they both have that in common, at the middle. So we're given on this particular problem 3 different sets, where we're given a universal set U, which is A, B, C, D, E, F, and G. And then we're given sets X, Y, and Z. And when we're asked to find the intersection, it means we're looking at these 2 sets, Y and Z specifically, and we're asking what they have in common. So what elements do they have in common? B and C. Yeah? So when I write this out, it's a set, so it will be in curly braces, and it's the set with the elements B and C. Okay, intersection means just like what you've seen it mean your whole life. All right, the next one is union. Union actually looks like U. So the union of sets A and B, written A union B, is the set of elements in A or B or both. And the set notation reads the same way. A union B is all X, such that X is in A or X is in B. And I know the notation doesn't say or both, but within mathematics, that's what the word or means, either or both. So the verbal picture that we had for the last one talked about the intersection of streets, right? And it having the same context. The verbal imagery you should have in terms of union should be that of a marriage. Okay, so when you get married, one of the things that's said in most ceremonies is that you are now one, right? What does that mean? Well, it means that if you had children before, now you both have children. And if you had debt before, now you both have debt. And if you have assets, if you have money, you now both have money. You get it all, right? It's like the yours, mine, and ours. Okay? It was yours. This was mine. Now it's all ours. Everything is ours. So you get the whole collection, the whole kit and caboodle, whatever. So when we're looking at these same sets that we had before, and we look at Y union Z now, so here's Y and here's Z, we're going to list everything in either set, but we don't list things twice, right? So if they both have B, we're not going to list B twice. We're just going to list it once. So you can go in any order. The order is irrelevant to what's going on. So if you want to just list everything in Y first, A, B, C, and then move over to Z and just continue on with what you already haven't listed. So I already listed B, I already listed C, so now I have D, E, F. Okay, start to finish, I get them all. Is that all right? So we have things they have in common, that's intersection. We have the collection of all the things, that's the union. And the last set operation we have is called the difference. Difference of sets. So the difference of sets A and B is written like subtraction. So A minus B is what it looks like, is the set of elements belonging to A and not to B. And that's what you see with the set notation. A minus B means X is in A, but X is not in B. After we do this example, I'm going to go back and show you pictures for these two that go along with the Venn diagrams. So what's our verbal picture? Well, if our union picture was, the union was talking about marriage, right? Collecting all of it to begin with. This is the right before we get married. Right, this is what I'm bringing into that union. It's the stuff that I had beforehand. Right, that was uniquely my stuff and stuff we didn't share, right? What did I come into that relationship with? Nothing we had in common, doesn't count. Nothing he had or she had, whoever the person was, doesn't count. It's what I brought into the situation. So when you're looking at this, another picture you can think of, or not picture, but another word you can use is the idea of removal. So we will remove, or this is the removal of common items. So on this one it says X minus Y. So X is these 4 items. So whatever I write down, it cannot include anything more than this, because these are the items that are in X. The difference means what I brought in. Well, X only brings in A, C, E, and G. Doesn't get to add things to it. That's what it started out as. The only thing that can happen is the removal of the things it has in common with B, or with Y. So what of these elements are in common with the items that are in Y? A and C, right? They had A and C in common. So when I find the difference, I will only write down E and G. They're the items that come in with A that did not have a relationship or a connection to, with X, that did not have a connection to Y to begin with. I'll start with the picture on this screen for the Venn diagram. So what I want us to draw, and this is the same picture that we're going to draw on all screens, is that we're going to draw a picture that has overlapping circles inside of a rectangle. Those circles are going to be labeled A and B, and the rectangle is labeled U. So this is the same picture I'm going to have on all 3 of these. So if I have this description, A minus B here, what it's actually describing visually is this piece out here. The items in A that are not in B, they're not in the overlap. Okay? Now, if we go back, I'll go back to the intersection one as my first one. And we do the same thing here. Intersection means the overlap. So what part of this diagram is going to be shaded? Yeah, the middle, that sort of football-looking shape in the middle, right? This is the intersection. It's overlap. And if I'm doing the union, what would that shade? All of it, right? So I'm going to shade everything in A along with everything in B. The union gets it all. Okay, so we're going to have sort of a throwback to algebra for a second here and talk about ordered pairs. Ordered pairs are written in a set of parentheses, A, comma, B, where A is an element of the set A, and the lowercase b is an element of the set B. A is called the first component, B is called the second component. And in general, just switching the order of things is a different point, right? So like think in terms of, algebra, the location for the point 1, 2 is not the same as the location for the point 2, 1. Now, if you talked about 2, 2, it would be because they match already, right? 2, 2 is equal to 2, 2. So a Cartesian product is simply the collection of all these ordered pairs. Everything in set A paired up with everything in set B. So here's the verbal description that you're going to go with on this one. Like what you're thinking of. This is speed dating. Okay, speed dating. Speed dating is the idea that you've got, and we'll go with equal numbers, though that doesn't have to be equal, but if you had 5 gentlemen come into the room and 5 ladies come into the room and you wanted everybody to get to know everybody, right, you'd pair people up one at a time. One guy and one girl, they would talk to each other for like 5 minutes and then they switch. And then they talk to somebody else until everybody has a chance to meet everybody. And the question is how many different pairings or what are the different pairings that you would have if you created that kind of a speed dating environment. And that's what it looks like when you do this. So we've got our set X and we've got our set Y. They don't happen to be the same number of items. That's okay, they don't have to. But what we're going to do is we're going to pair up every item from set X with the items one at a time in set Y. So this actually looks like a collection of ordered pairs. So we'll start with A. I can pair A up from set X with the A up in set Y. Okay, that's a pair. I'm just pairing them up one on one. So I can make a set or make an ordered pair AA. I can also pair up A with B. So I have an ordered pair AB, or A with C. And those are all the ways that I can take the A from set X and pair them up with items in set Y. And I can do the same thing with the next letter element that's in set X. So that's C. So what are my ordered pairs I can make with C? CA, CB, and CC. And in some sense, I'm sort of like ticking these off, right? I've done A, I've done B, C. Now I'm ready to do E. Well, I can make pairings with E and A. E and B, or E and C. That's all my pairings be. And then I can do the same thing with G. So I can do G and A, G and B, G and C. And if I'm asked to find the Cartesian product, this is the Cartesian product. It is a collection of ordered pairs. Now there's a connection, though, between how many items are in set X and how many items are in set Y and how many items end up being in the Cartesian set. How many ordered pairs are there here? 12. How many items were there in X? And how many items were there in Y? So what seems to be happening? It's multiplication. And that's exactly what's happening. So the cardinal number, that is how many of them there are, in a Cartesian product A cross B, is really the number of items in A times the number of items in B. So if you're simply asked, like on number 5, to find the number of items, while you certainly can list them all out like you did here, that is not what the question's asking, right? This question's just asking how many of them are there. So be very careful to read the question well. What's it asking? Is it asking you to find the collection of ordered pairs? Or is it just asking you how many ordered pairs are there? So this is the same XY, right? It's the same Cartesian set that we looked at before. But this question's just asking us how many of them are there. And if all I'm asked is how many of them are there, this is just asking number of items in X times the number of items in Y. And you guys already did that with me just a moment ago. You found 4 and 3. There were 12. So if you just ask for number of items, this is the shortcut to doing it instead of listing them all out. Okay, all good? Okay, the next thing that's on your page is really just a nice chart to put it all in together. So if you're looking at your homework and you want to be able to like see the union and the intersection, you want to see them all at the same time, this is the chart for you. So this is a chart that shows complement, which we did back in section 2.1. And then all the rest of them are in here at 2.2. So we've got intersection, we have union, we have difference, and we have our Cartesian product. So I wanted you to have a place where you could put them all in one glance and have them all together. So I'm just going to let you write them down. This is no new information, just compiled in one place. Anyone still writing? A couple people? It's okay, just checking. I don't want us to move too fast. So the majority of what we're going to be doing, the rest of this section and in 2.4, is going to be using these ideas inside of a Venn diagram. Okay? So the rest of this section is simply going to be taking a Venn diagram and finding which part of the diagram we're talking about based on the symbols that we're given. And then we're going to use that idea in 2.4 to actually use some application problems and see how that is usable in a real life situation, like verbal situation. So we have, in the next example, two sets. So when we have two sets, it will be drawn the same way that I drew those other pictures, like so. Okay? Two sets, we draw them as two overlapping circles. We label them with whatever the names of the sets are. In this case, they are A and B, so they'll be labeled A and B, and the universal set U on the outside. What I'm going to show you for this particular example is a little bit overkill for this example, but it's going to make it a lot easier for examples that are more complicated. Okay? So just bear with me, and you're like, why'd she go through all that trouble? I knew where to shade to begin with. Maybe you do. That's great. More power to you. But you might not know where to shade when we get to this one that has 3. So here is a very step-by-step way to handle these that works all the time. What we're going to do is we're going to label each of the regions of my picture with a number. So I'm going to start on the outside of A with 1, the overlap with 2, the outside of B with 3, and then the outside of both the circles with the number 4. Now, these aren't really elements, they're just shading, they're just representing the region. Right? Okay. So here's what we're going to do. We're going to take what's being asked of us here and label which of the numbers are in those regions. So A complement means I want to list all the numbers that are not in A. So which of those 4 numbers are not in A? 3 and 4. 2 is in A. It's in the overlap still. So even though it's not in the specific region that's only labeled A, it is in the circle A. So the only pieces that are not in the circle A are 3 and 4. Then it labels B. Not B complement, but B. B means what are the numbers that are in B? 2 and 3. Okay, so far so good? Okay, and then we take note of how they're being combined. These are being combined with union. Union, right, the idea of the marriage, means that I take all of these items that I've listed and I mush them together in the same pile. But I don't list things twice. So 2 is listed, and 3 is listed, and 4 is listed. So, that should say A complement from the top. Okay, so everything that's listed here, all listed in one list. And then the answer to the question is to go back to the diagram and to shade in the areas that we've labeled with those numbers. So we're going to shade in 2. And we're going to shade in 3. And we're going to shade in this outer part, which is number 4. And there's a shading tool when you're working with Venn diagrams inside of my math lab, where you kind of click on it and it drops the color in each of the regions. So this is the answer. This is the work you're doing to get there. Okay, so nobody's grading your work on these, right? It's all inside of my math lab, which means that if you have another method you think that you like better, that's fine. Just be a little bit careful when we get to the harder ones because they get more complicated. Is that okay on this one first? Okay. So as previously mentioned, there are 3 sets on this one, A, B, and C. So what that means is that I need 3 overlapping circles. So it starts to look like, the Olympic rings, the way that they overlap. So you have things that look kind of like this. Whoops. We'll try to get it more centered. And we'll label them A, B, C. And we have our universal set U on the outside. Okay, so far so good? All right. I need numbers representing these regions, and there are more regions than there were before, right? There are. And so just so that we're all doing it kind of with the same numbers in mind, The way that I always number it is I go straight across the top, I go through the middle, I have the bottom, and then they have the outside. So there's nothing special about that. It's just for the sake of us all doing it the same way. I've got 1, 2, 3 across the top, 4, 5, 6 through the middle, 7 over here in C, and then 8 on the outside. Now, is this the only way these circles could overlap? Well, no, it's not. So if they give you some other picture to start from, you just use the picture that they give you, and you put the numbers in for however many regions you have, and you do the same operation. There's nothing special about this particular picture. This is just the most complicated picture possible with 3 circles that we're working on. Okay, so we're going to start inside the parentheses, and inside the parentheses it has the A intersect B. So I'm first going to write down all of the elements, or not elements, but the numbers that are inside of circle A. So what numbers do I have located inside of circle A? 1, 2, 4, 5. Is that okay? All the numbers inside of circle A. How about circle B? What are all the numbers inside of circle B? 2, 3, 5, 6. And inside the parentheses, right, we're working like order of operations, that's why we're doing the parentheses. What does that symbol mean? Intersection. And intersection means where they intersect across what they have in common. So which items do they have in common? 2, whoops, to shade it, 2 and 5. So this is 2, 5. Now, working from the inside the parentheses out, I'm moving on to C. What is C? Well, what items are in circle C? 4, 5, 6, 7. Is that okay? The last thing it says is that I'm going to take the A intersect B that I found out just a moment ago was 2, 5, right? And I'm going to do that with the union with set C, which I said was 4, 5, 6, and 7. So what does union mean? All of it together. So I consider this entire list and this entire list, and I combine them into a combined list without listing things twice. So what do I have in this list? 2, 4, 5, 6, and 7. And then what will I do for my answer? I'll shade those regions. So I come back up here and I shade 2, 4, 5, 6, and 7. Okay. The last one's the most complicated. What makes it complicated is that, yes, it's got 3 circles like this one did. But this one was in some ways kind of friendly because there weren't any complements, right? A, B, C, no complements involved. But the next one has the 3 circles and it has complements involved, which makes it more complicated. So we're going to draw our rectangle. And I should have copied and pasted and didn't. We're going to draw our 3 overlapping circles. Oh, that wasn't what I wanted to do. And we're going to put our labels in, A, B, C, and union. And we're going to put our number representations for the regions. 1, 2, 3, 4, 5, 6, 7, and on the outside, 8. Okay, inside parentheses. The process always goes in the same order. We start inside the parentheses. I have A. So what numbers are inside of circle A? 1, 2, 4, 5. We did that one before. Now it doesn't say B, it says B complement. B complement means what? All of them that are not in B. So what numbers are not in B? Yeah, 1, 4, 7, 8. Good job. And then what does the operation say that I'm going to do to combine these? Intersection, which means what they have in common, where they overlap. What numbers overlap? 1 and 4. We have 1 and we have 4. And then on the outside I have C, right? So we'll look at C. What numbers are in circle C? 4, 5, 6, and 7. And if I combine it all, yes, ma'am, sorry.
My paper says C complement.
Do I have a typo? Okay,
I didn't know which one.
let's fix it. My slides should match your papers. Y'all have far more papers than I do. We'll fix that. Okay, C complement then, thanks. What elements are in C complement? Numbers are in C complement. 1, 2, 3, 8. Perfect. Okay, so we have the A intersect B complement now, and it should be the intersection of that with C complement. So intersection means what they have in common. So I'm comparing this list down here, which has 1 and 4, with this list here, which is 1, 2, 3, and 8. It's just 1. And up in my picture, I would just shade 1. Any questions?